the smart introduction to messaging. It's pretty crowded in here because of the delicious pizza. And today I would like to tell you something about messaging. It will be like a general talk. I will not talk about any concrete technology, but I will try to explain the principles of messaging. I will try to explain what it is, why is it useful, and where you can use it, and when you should not use it. So I'd like to start with the definition of messaging. So for our purposes, it's sending some data or messages between applications using some middleman. So if you are a client and you are just calling a server, then that's not messaging. The important part is that you have the middleman. It's called message broker. So it works like this: a sender or producer sends the data to a queue, which is like a buffer of messages. And on the other side, there is some receiver or consumer that reads this data from a queue and somehow reacts to them. So the whole definition, including some like official terms, is written like this. So that's the messaging. To show you a little small picture, it looks somehow like this. You have a producer, which can be any program that wants to inform the others about some changes, or it wants some job done. But it doesn't know who is interested in these messages. So it just publishes the messages into a queue, which you can see here, like this red rectangle. And then the messages are read by the consumers. One important part is that the queue contains these messages, and when the consumer reads the message and processes it, then the message is removed from the queue. So each message will be only delivered to one consumer if everything goes correctly. So why would you actually use messaging? There are a couple of reasons. I will talk about all of these later in the presentation. So this is just really a teaser, a taster of the reasons that you might want to consider. One of them is lower coupling. So the producer does not need to know about the consumers. It doesn't even care. It just has some information and wants to share it, or wants some job done. So that's all it needs. It allows you asynchronous processing, and by that I mean like really asynchronous, not async await. So you just schedule a job somewhere, and some time later, some worker or scheduler comes and takes the job and does it. It helps you with higher availability of your system. It allows you to do load leveling. So if you have some tasks that you are receiving in bursts and your system is under a lot of stress, you can use the message queue to actually take these messages and process them in a level fashion. So you don't need to be prepared for this big Black Friday loads and stuff like that, and helps you with scalability. There are several messaging scenarios that I would like to tell you about, and one of them is point-to-point messaging. That means that one message is produced and it is sent and consumed by one consumer only. Then we have publish-subscribe messaging. This means that one message is sent and received by multiple consumers. Right? Think like weather forecast or some news or chats. And one thing that's also possible is asynchronous request reply. So you send some query, you need some answer, and someone will answer it and send you the response back. What I will not talk about, but is also like part of messaging is data streaming, which is used for large-scale telemetry for Internet of Things. This is actually like a special topic that needs some special software and special knowledge. So this is not going to be covered here. Okay. So let me first tell you something about point-to-point messaging. As I said, this is it looks like this, right? It's like this. You have one producer, and typically you want this is used for processing commands. So you have some work done, and you need somebody to do it. You don't care who does it. You just have some job that you need to have done, and you don't even care about the result. You just need to trust that somebody will do it. So that's why you use where you use point-to-point messaging. So you have one producer and one consumer that will actually do the work, and you need, of course, the message broker, the queue. And this sort of pattern is called also a work queue or task queue. So the important thing is that each message goes to the queue and is processed only once. If everything works correctly. I will also like to show you what happens if something doesn't work correctly. So you can use this if you want to calculate some reports, for example. You want to send emails, or you want to do something that takes some time. So basically anything that you don't want to do immediately and synchronously, you just send to the queue and it gets processed a bit later. So the big advantage of this is that your user does not need to wait and just watch the loading screen, like processing, and wait for several seconds or minutes. And also, the consumer can be on a different hardware. So you can have a web server that places these tasks on a work queue, and then a different server that will actually process them. So you can sort of scale the load between hardware. Okay, so like I said, the important part of this pattern is the queue as just a buffer of messages, and another part, or I can say component of it, is the message itself. So message is basically just some byte arrays, just some content, and some data that you are sending, and it consists of headers and the data itself. In the headers, you have various information similar to HTTP protocol. Even but you get different set of headers. Of course, you might get some content type or some expiration. Maybe some of the messages are not so interested if they are not processed quickly or in a few days. So that's the point-to-point. The examples I already told you about. So I will show you some quick demo, and I will not show you actually any codes, because like I said, this is supposed to be generic talk. But I am using RabbitMQ, so later you will be able to check the codes if you are interested. So suppose that you have, well, I don't have any job to actually do. I don't want to generate any reports or so. So as a placeholder, I'm going to calculate Fibonacci numbers. Everybody knows how Fibonacci numbers are calculated. It's not really that important. And so we will have a server that will listen to some Fibonacci requests, and because this is a point-to-point, we will have some program. I'll call it Fibonacci requester, and that's the producer that wants the job done. It just wants some Fibonacci numbers to be calculated. It doesn't actually care about the result. It just wants it done because somebody else needs it. So if I run it, you can see this is maybe a bit too big. You can see that the producer is requesting some Fibonacci numbers, and the server here is receiving the requests and computing the numbers, and it's just writing them down on the console. And you can see that the producer is requesting the numbers a bit faster than the server is able to calculate. So if you want to process these numbers or these jobs faster, all you need to do is just run another server. So try to show you that. Cluster. And now you can see that each of these two instances will get some of the jobs. The one on the left is getting the odd numbers, and the one on the right is getting the even ones. So that way you can sort of spread out the load and do everything a bit faster. If you need to calculate more and more, you can just add the servers. But you don't need to. Everything is in the queue, and you can just take your time and calculate it. So eventually, it will be done. What you just need to do is you need to be over time. You need to be faster than your clients. Otherwise, you will be calculating like really old jobs, and you will get more and more behind. Okay. One more thing that I wanted to show you is that the message queues are actually all about reliability. Because you, as a consumer, you have a job and you want it done, but you don't get any information that it was actually done. So you need to trust that happens. And this is the job of the message broker, is to make sure that well, of the message broker and of you as a developer, is to make sure that all jobs are done. So that means that if I were to kill one of these in the middle of the calculations, let's say this one with the even numbers, it's now computing Fibonacci 76, 78. Now I will close it. Now in a few seconds, the remaining server should pick up that job and try to calculate it. Okay. It's like 77, 79, 81, and now maybe it will be 83. Oh no! So you see that there's 78. So this job was not finished by the first worker, but it's now being done by the second worker. This is actually sorry, a nice demonstration of how the delivery works. Because in the context of messages or of messaging, the message is not considered delivered when it actually reaches the consumer. It's considered delivered when it reaches the consumer, and when the consumer processes the job, and when it acknowledges to the broker that, yeah, I'm done, this job is finished, you can remove the message from the queue. So that's a really important distinction. Okay. It has also another impact on you, and that is you need to be prepared that you might get the same message twice or several times. So you need to design your applications in such a way that the processor, the worker, is idempotent. That means that it can receive the same message several times, and it always gives out the same result. Because with the Fibonacci numbers, it obviously doesn't matter. But So, I don't know, if you want to transfer money between accounts, you wouldn't want to transfer the money twice or 3 times. You just need to do it once. That's the point to point. Do you have any questions regarding that? No. Yeah?
The Fibonacci number, there was some automatic load balancing that you run to servers from another address where the deals. The numbers.
Yeah, you mean like the way they are distributed? Mm-hmm. Well, there are actually like several different approaches. One of them, yes. Yeah, this concrete case, this uses in this concrete case it works like this. There's a prefetch, so the server it takes 3 messages at a time and it processes them, and so while it has the messages, it will not receive more of them. It just has 3, and when it calculates the one of them, then it has like a free slot, and it will get another message. In effect, they will just alternate because that's because the job is calculated correctly. But if some of the numbers took longer, and it was not like regular. Say all the odd ones would take double the time. Then one consumer would just take his time, and then I would have to draw it. And it's just so. Well, the consumer takes the messages when it's ready to take more of them. That's what I'm trying to say. So the broker does not like push the work if they are not prepared.
Was it just lucky that it got on one calculator on the odd numbers and on the second on the even? Because well, I don't understand how with 3 numbers in buffer it could take on the odd in one and on the even in other.
Well, that's because the buffers the numbers are just increasing. So all the applications are at the same level. And when I started the second one,
that the other one had 2 odds and 1 even, or 1 even, or 2.
I would have to. I would have to check.
Or it should have.
But no, this is the second one. Yeah, so you can see. Yeah, you can.
Until you start the second one, it has 4.
You can see.
6.
Yeah, you can see. You can see here. Yeah, but it starts with 3 that are in sequence, like 3, 4, 5.
I didn't know that.
And then when they release, they will just alternate because it's sorted out. Yeah. This is a good question. You got me confused a bit. But so that's this one. I'm going to let it run. Okay. So next, I would like to demonstrate the high availability and how the queues will help you with that. So here you can see an image of a fictional application. It's for car sharing. And let's say your main business is to lend cars to drivers. So you earn money when they reserve a car and they drive it and they pay for that. So the use case for reserving the car would look something like this. The user goes to your car sharing application, and that application actually makes the reservation in some other reservation system and sends an email informing the user, this is all now. This is really simplified, so just don't look into it like more in a complex way. And without the message queue, you might design the application like this. So the user books the reservation, and this all happens synchronously. So you call the reservation system. When it's done, you send the email, and when it's done, you tell to the user that yeah, we are done. You have your reservation here. Now you want to guarantee some availability to your stakeholders or to yourself if you are the one running the car sharing application. And now the problem is when your application has something like, say, 99% availability, but the other systems have different numbers. And these also influence your availability. So even though you might be running, when the reservation system is down, then you cannot make the reservations. So that's a problem because the drivers are not booking any cars and you are losing money. And actually, would you guess or calculate the overall availability of this system, of this solution? No, no guesses. All right. Yeah. So it's really 96% because for your booking to work, all three of these systems have to be up at the same time. And actually, the difference between 99 and 96% might not seem that big, but it's tremendous. It's like instead of being 1% of the time down, you are 4% of the time down. So that's a huge. So what you can do instead is use a message queue, and then the solution might look a bit like this. When the user goes to your application, he makes the reservation, and you just store it in the message queue, and you tell him, yes, thank you for your request. We will process your application or reservation, and then the message gets stored here in the queue, and you have a worker or several workers that will be processing the messages, and one of them takes the reservation request and tries to call the reservation system. And now it doesn't matter that maybe the reservation system was down when the user tried to book the car, because the reservation will be done a bit later. When this worker tries to call it and finds that there is an error, he can just retry later, after a minute or after several minutes, with some delay. So it might put the message back into the queue to be processed a bit later. And the same goes with the mail server. So in reality, this would be like one process that goes one after another, but I simplified this. So overall, the availability of your system will stay at, well, of this particular use case, will stay at the 99% that you are guaranteeing. Because I think this is actually really strong selling point for the message queues. Because if you rely on some other external systems for your use cases and you call them directly, synchronously, then you also rely on them being available, and if they are down, then you are down also. So you cannot guarantee anything, basically. So that's one thing. Another thing that the messaging brings you is load leveling, which works like this. The producer, or you have many producers that are ordering something that's like a Black Friday is coming soon, right? Something like that. So a lot of people will go crazy and just need to buy all the clothes and shoes and I don't know what, and they will just throw everything they have at you, and you need to be able to actually process all these requests. So instead of necessarily buying a lot of hardware or scaling up to, I don't know, hundreds of instances. Well, probably not as an issue, but for something higher, you can just store the messages in a queue, and you can process them in the background. You can process them at a steady pace. So you will do, I don't know, 60 a minute, it's not that much, but you will catch up at night when nobody's ordering. So that's the purpose of load leveling. Okay. So to summarize the advantages of the point-to-point, there's lower coupling. You don't, you have a job and you don't care who does it. You just know that somebody will do it. It allows you the synchronous processing, and even I heard like an opinion, it's kind of strange to me, that you can collect these all these requests during the day, and you can just run the server at night and process the messages at night, just to save on cloud costs or stuff like that. So, I'm not sure if that's worth it, but it's an option. It allows you to have higher availability for your critical use cases, which usually the commands are critical, because that's what you want your users to do. You can cache the queries, but they don't earn you money, mostly. And it allows you some load leveling. Okay. So that was point-to-point messaging. If you don't have any questions, I will move to the other scenario or pattern. And it is called publish subscribe. Like I said, this is for cases where you have one producer and many consumers of the same message. So unlike with the point-to-point, where you process the commands, you usually don't want the same command to be processed many times. So this pattern is used for processing events. So think about I don't know, sending notifications that you changed something. You modified the car in your car sharing application, or you have a Slack and you want to send the message to everyone in your channel. You have, I don't know, Instagram, you want to take a picture of the pizza that you are eating and shout to the world, hey, I have this great pizza. It's, I don't know, with cheese. In the context of publish subscribe, the producer and consumer are also sometimes called like publisher and subscriber. And the architecture of that looks a bit different, because it's still the fact that only one consumer can consume one message from the queue, that still holds. So you need to somehow duplicate the messages so that each consumer gets the message. And you do it by having this component. This is called exchange in RabbitMQ. And if you are working with Azure Service Bus, then this is completely renamed, but the principles are the same. It might be called like a topic. And the exchange is something like a router. It gets the messages, and according to some rules that are inside the exchange, it decides where to send these messages. So it might be set up to broadcast the messages to everyone who's connected to the exchange, for example. Or maybe you are interested in whether just in Prague, you're not interested in whether in Dubrovnik or Bratislava. So you just subscribe to a subset of messages, and the exchange knows that it should send you messages, weather forecast for Prague, and that's what you get. Okay, I'll show you demo again with the Fibonacci numbers. So we are still calculating. You can see that we are still calculating the old jobs, the old Fibonacci numbers that the requesters wanted. And but now we have somebody who is actually interested in the result. He wants to know what the values are. This application doesn't actually care what information it gets. It just wants to know everything. That's called Fib Listener. But if I run it, sure, let me. Yeah, it's mine. Yeah. Now you can see that the server is calculating numbers, and the listener is getting the results. And if I run another listener, then it should get the same numbers. What's wrong here? Restart this. And more of them to get some information. Oh, you probably have the queue empty. Okay, so let's. Here you can see that both of the listeners are getting the same information.
Did you stop before the very first calculation?
I'm sorry?
Did you restart the very first calculation because it's just starting from 0 again?
Well, yeah, the calculation is just from 0 to 100, and it goes in a loop. I wanted to keep the numbers, how long these are calculated in some sane values. Okay, I'm thinking what I wanted to show you. Oh yeah, one more thing I wanted to say is that you can see that these consumers, they are getting their numbers from all the servers. So actually, even though you have 3 servers, these consumers are getting numbers from all of them, because they are, well, by accident and by some regularity in these jobs, they are calculated in order, so they are, you can actually see them being calculated like this. And even though the calculation takes 6 seconds or more, the pause between them is not that big. So we have 3 servers that work with the numbers. So this is really just a simple principle. There's not much to it other than the exchange, other than the fact that you need to duplicate the messages. But the advantages is that you have much simpler communication. If you need to tell somebody about something, you don't need to know his address. You just send it to the queue, and everybody who's interested in the results can just read them there. Think about the differences as between sending a mail, like a snail mail, to each of you, or you can just put it on the board and everybody reads it. And the producer does not need to know anything about the consumers. This is actually really useful if you have, even if you have like a normal regular architecture, but you are load balancing and you might have like four web servers, and maybe something changes in your system, and these web servers need to clear their caches. So you either wait and clear the cache and reload the data every minute or every 20 minutes, or you broadcast the messages and then they can reload the data and be up to date immediately. Oh yeah, do you have any questions regarding this? No, I thought so. So here's the yeah, because this is really simple. I'm sorry, this is called interaction. It is like all the patterns are simple, but it's worth knowing about them. Okay. One more thing that I want to show you is the asynchronous request reply, and this is actually what you want to do if you want to do both parts. If you want to execute some job and you want to see the result. So first we saw the commands, then we saw events, and now we will see queries. You are asking for something. I have to admit that I actually never really use this in production. So this is sort of a bit theoretical for me. It has some disadvantages, but it might be useful in some contexts. For example, in the context of microservices, where you might have several different services that give you data. Then with this pattern, you don't actually care who gives you the answer. You just ask the question and somebody will answer, hopefully. So this works like this. You have a producer, or let's call it a client, and he sends a message to some queue. This is similar to the point-to-point processing, this part here. But the message has some special parameters. It has a header reply to, which is like a return address, backward address. It says, yeah, when you are done with processing my query, and when you have the information, let me know and send the data to this queue, and I will pick it up there. Then the server gets the message, calculates it, and when it's done, it replies to this queue. And also, the message carries some correlation ID, which identifies the request, so you know where this answer belongs. So you can do this. You can use this to simulate the classical client-server scenarios. It has some advantages, in the context of microservices, you don't need service discovery, because you just have the message broker, and you call what you need to know, and somebody answers. It's also a bit more fault tolerant. When the server is down, then your client still is working, and you might not even notice if the downtime is short. It's like a second or 5 seconds, and you will never know because you get your answer. Maybe a bit later, but you get it. Now I'll again show you some demo. All these. Yeah, now because we have the queues pretty full, I'll first clean them. So you can see here is the administration interface for RabbitMQ. So we have this is the queue Fibonacci calculate that has all the messages, all the jobs that are for us, and there's 220 messages waiting to be calculated. So I will do something that you will probably not do in production. I will just delete those messages, and then we can run our server, and we can run the client. The client works like this. It's constantly asking for new numbers, but unlike the requester, it also waits. Waits. It also wants the answers. It's not waiting to receive them. So it's just listening to the reply queue, and when it gets the message back, it writes it down. So for the first few numbers, you can see that the calculation is quite fast. So you request it, and you get the number, or you get the reply quite fast. But soon you will see that the requests go much faster than the server is able to calculate. So that way, also again, the queue begins to fill up, and the server falls down, falls behind. And we can again fix this with running more servers, which I'm not going to do now. So, like I said, this might be useful to you if you have many services that you need to well, then you need to change, and you don't want to be waiting, and you need to be able to deploy them and take them down for a while. There's some advantages. Also, what I mentioned is that it all balances naturally. It's the same as with the jobs. If you want more power, you just add more servers and more computers. The thing is, I'm not really sure how much useful this is in practice, because it's a bit more complex, and it also has some other problems. You need to be you're not doing just simple calls and getting the responses, but you need to somehow match the messages. You need to be aware that you still need to be aware that you sent a request, and you need to somehow handle the timeouts, for example, yourself, and you say after like 5 minutes, okay, I give up. I'm not waiting anymore for this.
This is actually very useful if you have unreliable network.
Mm-hmm.
Because
But
when you need to issue command, then you need to know that it was completed.
you mean like between?
I don't know, toggle lights in the other building. It's over Wi-Fi, battery is bad. You need to know that lights are out.
Well, but you still need to be able to reach the message brokers.
Yeah, and you have one message broker on the command side and one on the executive side. So they are.
Yeah, I see. Yes. So the communication is actually between the brokers, and not directly between. Yeah, that's nice. Well, like I said, I never used this request reply. What we did actually when we wanted some information back, we just did a simple broadcast, because we only had a bit simpler systems. We didn't need to really target this one application that sent information. Okay. Now, sorry. One thing you need to think about is how you handle the faults in the processing. Because I already showed you what happens when the server dies, that another server might pick up the changes. But sometimes, well, there are other problems that you might run into. For example, there's a bug in the server, and you get a message that you can't process, or maybe some external system is not available, or maybe you get a message that you don't understand. You just don't know what's inside, or you get a message that's expired, because it's some old message and it's no longer relevant. So the things you can do is you can either retry the call. It makes sense if you call some external system and it fails down, you can try again. But let's say that the problem instead is a bug in your consumer, so you will be getting null reference exception on each call. And what you don't want to see is that you get a message, you fail, and the message goes back into the queue, and you do it again and again and again, and you are just recycling the same message, which you cannot process. So in that case, you have other options. You can either abandon the message, you can just drop it and say, okay, I'm sorry, I cannot process this. I give up. You stop. But this is also not ideal, because you promised to the consumer, to the client, that you will execute this job. So there's a third option that's called dead letter queue. Looks like this, and it works like this. You have a sender that sends a message to your queue, to your channel, and for some reason you are not able to deliver the message. Either it's expired, or it's like I said, it's a bug, or maybe it's a poison message. A poison message is something that you cannot even decode. Maybe you are just reading JSON messages and this is XML. So what do you do with it? Nothing. You just can't understand it. So instead of dropping it, you will send it to a different queue. It's called dead letter channel or dead letter queue, and the message just stays there. And now it's your job, well, as the administrator, to check periodically the dead letter queue and see if there are any messages there that you might want to handle. So you need to be monitoring this and somehow deal with the problems. And this is like superior to just logging the problems, because you still have the whole messages, and maybe you finally fix the null reference exception, so you can write a simple script that will reroute all the messages back to the processing channel, and you will rerun and reprocess them again. Or you might decide that you as a human that yeah, this is really old, so you just drop those. So if you do the messaging, I think this is a good thing to know, and this should be implemented there. Now with the dead letters, like I told, you need to monitor it. So I just have simple examples what you might be monitoring with the messaging, because this is a bit different to the other systems. You might need to look at the number of messages in the queues, like you need to look at in the counts, the trends. You need to check if there are any queues that have no consumers, that they are just growing the numbers. What I want to show you is the administration application. The RabbitMQ has a really nice one, where you can see an overview of how many messages are there ready to be processed, and how many messages are actually unacted. That means that they are being processed right now at this time. So there's nothing running there. And see, and you can analyze all the connections here to the queues. You can see, okay, maybe I have this queue with 234 messages, and I will see that the number is growing. So you will know that you need to add some consumers. So there are also, of course, some disadvantages to messaging, which I think the main disadvantage is the increased complexity. Sometimes you just don't need such a big thing. You have really small application that can do with the synchronous requests, because it's really fast, and you don't need such reliability, or you don't need any asynchronous processing. Your message queue is a single point of failure. If it doesn't work, or if the broker is down, then you are out of luck. This is, I think, is the same with as with databases or some other things. You just need to rely on that. And it's harder to track the program flow. If you are sending messages here and there, and something might be happening, and you're aware what. But still, I think it's a really useful pattern. So I wanted to actually ask you. Well, you already told me that you used it. Do you have an experience with messaging? Are you using it in your systems?
in the way like the worker processes behind and synchronous process the request.
Yeah. So well, some people do. And I'm sorry.
I don't know.
I know. Yeah. So do you find it useful, or do you have any problems with it? Something that was that you thought, yeah, maybe I shouldn't have really done this. I should have done it the easier way.
Only problem was when we wanted to later migrate it or make it synchronous, basically, at the end. Yeah, then it was quite painful.
Yeah.
And the requirement changed during the time, and then some tasks had to be synchronous. And it was
yeah. So
you need to really
you had
wait basically, and
different tasks that you need to cover. Yes. Yeah. Yeah. That's a good problem because what the messaging is about that all these messages are like separate. There are some ways to group them, but usually you need to look at them as separate tasks. So I just summarized here some questions. If you would someday consider using the message queue, or you will need to choose one, then what you should be thinking about. I don't want to go through those. It's just like a quick checklist. What do you want to check? Because the messaging systems, there's really quite a lot of them. There's a good page with a summary of them. It's called Queues.io. It's a long list, and there are like a lot of differences between them. Some of them are really closer to what I showed you here, just like the RabbitMQ or Azure Service Bus, but others are quite different beasts, and you might. Depending on your use cases, depending on your needs, you might need something else. So here's also a list of some interesting projects that at least for me are interesting. So there's Apache Kafka. It's like the event streamer or data streamer. So this is meant to process big amounts of data. I think like hundreds of thousands of messages per second. You can't normally do that with Rabbit or probably Azure Service Bus will be able to do it, but I'm not sure how pricey that would be. Or you have some like communication protocols here, NSQ, 0MQ. So if you're interested, I think this is a nice list of products to check. So that's all from me. If unless you have any questions. Okay, so thank you for your attention.